What I would like to talk about in the next couple of minutes is why angle of attack is information that allows you to be a better pilot. If you think about it, our number one responsibility as pilots is to maintain control of the aircraft at all times. And that's what we try to do, and that's what we mostly do. Occasionally, though, someone loses control. That's called LOCI in accident terminology, meaning loss of control in flight. And here we see a good example of that. We've got two guys on final. The second guy is obviously way too close to the first guy. He realizes that, and he's trying to increase his separation. And he's trying to do that either by slowing up a little bit or by initiating a shallow S-turn to give himself a little bit more space. Unfortunately, it doesn't work out the way he had hoped, and there are tragic consequences. So here he's starting his bank, and there he loses control and goes into the ground. What I'm going to discuss today is first give you some information about loss of control, which is by far the biggest cause of accidents and fatal accidents, not only in general aviation, but even in commercial aviation. Then talk about angle of attack, review what it is, and then talk more specifically about why it's important and better than airspeed to control flight in certain conditions. Then talk about what kind of angle of attack systems are out there and how does that information displayed. And then the last half of the talk will be a bunch of short video clips that show angle of attack being used in the cockpit for a variety of flight situations. If you look at the cause of accidents, and this happens to be from one source, and it's for general aviation, fatal accidents over a 5-year period, what you see is that loss of control in flight, or LOCI, is by far the largest contributor to accidents. In fact, if you combine all the other sources of accidents, like controlled flight into terrain, or unintended flight into IMC, or all the other things that we know are causes of accidents, all of those together are less than half of what the LOCI, loss of control incidents in flight, represents. Now here the plot is shown horizontally. The next plot shows similar data from a different source. It's plotted vertically instead of horizontally. There's a little bit more information. The yellow represents certified aircraft. The blue represents experimental aircraft. The purple actually represents turbine aircraft. But the trend is the same. LOCI, loss of control, is by far the largest single reason for general aviation fatal accidents. Now, because loss of control is essentially a pilot issue, you would think that the more experience a pilot or an aircrew has, the less likely they are to experience loss of control accidents. Well, if you thought that, as I did, you'd be wrong. And this is data for the worldwide commercial jet fleet over a 10-year period. And guess what? Loss of control, those trends in terms of causes of accidents, even for highly experienced flight crew, is pretty much the same as what it is for general aviation aircraft. If you look at where loss of control occurs in terms of the phases of flight, it occurs across the board, even occurs en route, where you might not expect it to occur. It's a little surprising to me that it's a little bit higher on takeoff than it is on landing, although you can consider approach and landing together to be more, it's more common than it is on takeoff. But the point is, it happens across the board in the flight conditions that we encounter. This is pretty much the same thing. It's a little bit more detailed. The red bars represent the percentage of all general aviation accidents represented in the various phases of flight. So basically you start with taxi, you take off, you climb, etc., you finish off at landing. And so if you look at the red bars, that's the percentage that is contributed in that phase of flight. If you look at the black boxes, those represent the amount of time that aircraft spend in these various phases of flight. And if you add the numbers up, if you look at everything in the black box, these red bars represent 70% of all general aviation accidents, even though that we're only flying in those conditions for 17% of the time. So a lot of loss of control happens at low air speeds, not too surprising, but that predominates the loss of control situation. And you can also look at these trends across time. What we're plotting here is stalls as a percentage of all fatal fixed-wing accidents. This is over a 15-year period. And you may make the argument that things have improved a little bit, but the fact is that in 2014, the rate of stalls was essentially no different than it was 15 years earlier. So not a lot of progress in terms of reducing those kind of accidents. Now, the angle of attack became an issue for the Navy about 70 years ago. where they were switching at that time, this is right after World War II, they were switching from propeller operations to jet operations off carriers. And they noticed they had a very, very high accident rate, much higher than they had with propellers. And there's a bunch of reasons for that. One of them is that these jets approached at much higher airspeeds, and it's still approaching on the same small carrier deck. An F-4 Phantom has an approach speed of 145 knots. Carrier landings are incredibly challenging. You're looking at a runway that's only 700 feet long, and that's really deceptive because the arresting wires that you have to hit, there are 4 of them, and they're only spread over the first 160 feet of that runway. So if you can't nail the aircraft within 160 feet, you're either doing a go-around or you're going into the water. And what the Navy found, and they studied this a lot, was that in order to do a successful landing, you had to maintain a very, very precise airspeed on the approach, plus or minus 2 knots, which is not easy to do. So they ended up determining that angle of attack made a much better flight metric to control the approach and result in a successful landing. So they also developed an instrument that would allow the pilot to visualize angle of attack, and you can see that here. So that's their angle of attack indicator, and you can see this orange circle here is representing when the pilot is on the ideal angle of attack for the approach, which is called on speed. And they defined on speed as a speed equal to 30% higher than the stall speed, but on speed is actually the equivalent angle of attack. It occurs at a specific speed for 1G, but on speed means you're at the ideal angle of attack for the approach. As a result of this, the Navy was able to reduce their landing carrier accident rate by about 50%. And not only the Navy, but ever since then, for about the past 70 years, both the Navy and the Air Force train their pilots to operate their aircraft in the approach phase using on speed. Unfortunately, general aviation has not followed suit for several reasons. So let's review what angle of attack really means. Angle of attack is simply the difference between the reference line of the aircraft, or the wing, and the direction of flight of the aircraft. There's a famous book called Stick and Rudder by William Langevin, and the way they describe it, it's the difference between where the aircraft is headed and where the airplane is actually going. And that relatively small angle is called the angle of attack. However, you can fly a specific angle of attack at any airspeed and any altitude, as you can see by these illustrations. You can be at red line and still be at a low angle of attack or a high angle of attack. It doesn't matter. What matters to the wing, and the only thing that matters to the wing for a fixed set of flight conditions, is what angle it is to the relative wind. Why is that important? Because the wing only knows what that angle is in terms of its ability to generate lift. Most airfoils only have about 20-degree range in which they generate lift. So it turns out that if you have an angle of attack indicator that allows you to fly a specific angle of attack, you're much better able to hold the conditions that you want to hold for specific ranges of flight or phases of flight. This is what the curve looks like, and what we're plotting here is what the lift generated by the wing is. You can say it's generated in pounds, versus the angle of attack. So there's some angle of attack at which the wing will not generate lift, and then as you increase that angle, the lift increases, usually linearly, until you hit the maximum condition. The stall is the angle of attack at which the wing generates as much lift as it's capable of generating. If you go beyond the stall, what happens is that the airflow over the top surface of the wing starts to separate from the wing, starting at the back, and then the more the angle of attack, that separation point moves forward along the wing. But the key is, once you hit stall or even go beyond stall, the behavior of the wing is very much different than it was designed to be, and you lose control of the airplane until you get the airflow going over the wing properly. Now, this is a figure that many of you might recognize from your pilot training days, and what it says basically is there are 4 forces acting on an aircraft, 2 in the vertical plane, lift and gravity, 2 in the horizontal plane, and when the aircraft is in steady state flight, and it could be cruise, and then the net result of all of those forces is 0 force. And if you have 0 force, you have 0 acceleration. If you have 0 acceleration, it means you're in a steady state condition. You're not changing your position either vertically or horizontally, or I should say you're not changing your speed either vertically or horizontally. But for our purposes, I'm only focusing on the thrust and the drag. And if you're at any specific airspeed, and you're in steady state conditions, whether it's a low airspeed or a high airspeed, the thrust and drag are equal, because that means there's no net force, you're not accelerating. Well, if you take the thrust and you multiply it by that velocity, that gives you the amount of power that's available, that's being generated by the propeller. If you take the drag and you multiply it by velocity, that tells you how much power is needed to maintain that state of flight. And in particular, I'm going to focus on the power required because that tells us a lot of important information. So what I've done is to calculate the power required curve for a Cherokee 180, the 1973 model that we have at Yale Aviation, 044. That airplane has a very specific airfoil. All the calculations are done for a standard atmosphere at sea level, so it's 29.92 inches of mercury, 59 degrees Fahrenheit. And it's also, those calculations are performed for the aircraft at max gross weight, which is 2,450 pounds, which you would achieve with 3 passengers, full fuel, 50 gallons, and some bags. Now, there's some implicit assumptions that are worth pointing out. One is that all of these calculations assume that the airplane is flying at 1G, which is sort of our normal cruise operation. But these values that I will show you come from the Pilot Owner's Handbook, or POH. So the numbers that you see here are what are in the POH. So what does that curve look like? Well, it's the power required curve is the dark curve I'm showing here. And it's important to note that this is for the aircraft with the flaps up or in the clean condition. So the stall speed for the airplane with the flaps up is 68 miles an hour. If we put the flaps down, our stall speed decreases to 61 miles an hour, and this is where that point lies on the power required curve. Now, in this particular case, I'm also showing you the power that's being generated at the propeller when the engine is at 100% power, 2,700 RPM. And so you can see that the two curves cross. The power required is equal to the power available for 100% power condition out here at 148 miles an hour, and that is what the POH says is the maximum speed of the airplane. Now you'll notice that I have a bunch of conditions that are noted here, and so let me explain why those are important to keep track of. We call those, by the way, key performance points because each one of those represents a flight condition that at different points in time we may wish to fly, and it's useful to fly. Obviously, there's the stall speed. That's important because if we hit stall or go beyond stall, we lose control of the airplane, at least until we can recover. And if we're low enough, we can't recover. Let's say we're a Civil Air Patrol mission, and we're doing a search and rescue over a given area. We want to maximize how much time we spend over this area. We have a finite amount of fuel on board, and so we want that fuel to last for as long as possible, in other words, maximum endurance. Then we want to fly at the speed for minimum power, because power is the rate of use of energy. And so if we have a fixed amount of fuel and we have minimum power, that gives us the maximum time that fuel will last. If we are taking off and are worried about obstacles at the end of the runway, then we want to fly at the maximum angle of climb, which is called VX. So we want to fly at that speed that gives us the maximum angle of climb. On the other hand, it's more common when we're in a cross-country, for example, that we want to get to cruise altitude as quickly as possible. And in that case, we want to fly at the speed at which we get the maximum rate of climb, which is called VY. Now, if we want to fly as far as possible, we want the aircraft to be operating at its most efficient point. And the airplane is most efficient when the ratio of lift to drag is the highest, or maximum. And so if we want to fly maximum range, we want to fly at max L over D. Now, if we have power and we're cruising, that means we'll fly as far as possible on the fuel that we have. If for some reason we lose power, now we're a glider, and we still want to fly for the maximum range given the altitude that we have. And so we want to fly at maximum L over D in an engine-out scenario when we're looking for a landing area. And then there's one other speed that I mentioned briefly before, and that's called on-speed or VREF. That's a very simple calculated speed. You take the stall speed, typically in the landing configuration, you multiply it by 1.3, and the resulting number is called VREF, and it's also called on-speed. That's a very important speed, and it also corresponds to a very specific angle of attack, and we'll talk more about that. You'll notice that for the Cherokee, the speed range that we operate at is from about 60 to 150. So we have a 90-mile-an-hour range in which the aircraft generally will fly. But these key performance points occupy only about the lower one-third of that operating range. And in fact, there's very little separation between some of these points, like between minimum power and stall in the clean configuration. And so it turns out that makes it more difficult to fly at these specific conditions because these key points are bunched up in the airspeed range. So It's difficult to hold a very specific airspeed within a knot or two using the airspeed indicator, especially if there's turbulence. And the other thing that happens is that the speeds that we want to fly at, the target airspeeds, change with all of these conditions. And these conditions change not only day to day for a particular flight, but even within a flight. So we're flying the airplane at different weights on different days, or even at the beginning of the flight and the end of flight. We experience G loads from both maneuvers and turbulence that we can't predict, but they affect how the airplane performs. And then, obviously, we're flying at different altitudes, temperatures, and pressures. Again, within a flight or day to day, these things, which are all kind of rolled up into density altitude, will change. And what that means is that the airspeeds that we want to fly these specific conditions at will also change accordingly. Now, the good news is that the density altitude effects are actually already accounted for in the airspeed indicator. So we have to worry less about that. So our airspeed indicator we don't fly using true airspeed. We fly based on what the airspeed indicator says, and the airspeed indicator tells us indicated airspeed, not true airspeed. It turns out that the airspeed indicator is essentially a pressure gauge. And so what it does is it measures the dynamic pressure from the pitot tube, and it does a conversion of that into speed or velocity. But it does that with it's calibrated so that that is accurate only for a standard atmosphere. But it does not account for two things that are very important. It does not account for the weight that the airplane is operating at, and does not account for the G loads that we're experiencing during flight. So let's illustrate the significance of that. And I've got two scenarios. In one case, we're flying with 3 passengers, full fuel, and some bags, so we're at 2,450 pounds, which is the max gross weight of this aircraft. But in the second case, we only had the pilot, and we have about 10 gallons, or roughly 1 hour's reserve in the tanks. Hopefully that's at the end of the flight. But in any case, we're substantially lower weight than max gross weight, about 30% lower weight. So what is the significance of that? Well, if we're at the max gross weight, our stall speed with flaps is 61 miles an hour, true airspeed. However, if we're much lighter, 1 person and 10 gallons of fuel, our stall speed is actually dropped to 51 miles an hour. So that stall speed is 16% less than it is at max gross weight, and these are the numbers that are in the POH. And in fact, you will not find in the POH how to calculate what that is. There are rules of thumb to do that. It's not that complicated, but it's not in the POH, and I would postulate that many pilots don't make those kind of adjustments to their target airspeeds based on weight. Now, again, this is the same curve I've shown you before. This is the curve at max gross weight. Now let's look at the curve for a lighter weight. And so the shape of the curve is similar. This is the curve at the lighter weight. And for reference, I'll show you what the POH curve looks like, which is this curve here. And the curves have similar shape, but they're different. And they're different in 2 respects. First of all, you'll notice that you need substantially less power at the lower weight than you do at max gross weight. At max gross, we need roughly 60 horsepower in order to maintain level flight at these lower airspeeds. When we're flying much lighter, we need less than 40 horsepower. Now that's interesting, but that's not really the main point of what I'm trying to say. The much more significant thing is that all of these speeds for the lighter weight have decreased by 16%. We previously talked about the fact that the stall speed with flaps went from 61 miles an hour to 51 miles an hour. If you look, for example, at the speed for max L over D, that went from about 91 miles an hour at gross down to about 77 miles an hour. So you're talking 14 mile an hour difference because of that weight change. Now, what that tells us is if we fly the way our actual conditions tell us we should fly, the stall speed is 51, VREF is 1.3 times that, or 67 miles an hour for this weight. However, let's say we don't know that, or we can't figure it out, or we don't think it's important, and what we do instead is we say, well, let's fly it by the book. The book says the stall speed is 61, 1.3 times that, says VREF is 79 miles an hour. So suppose we fly the approach by the book instead of what we really should be flying. What's the consequence of that? Well, now we're flying about 20% faster than we should be flying, and the energy that we're carrying, kinetic energy goes like the speed squared. So if we are flying 20% faster than we should be, that means we have more than 40% extra energy than we really need. The only way we can dissipate that energy once we touch down is through the brakes. They convert kinetic energy into heat, and they have a finite, limited ability to do that. And so it will take us substantially longer to stop if we're carrying that much extra energy. Now, if we're flying out of New Haven that has a 5,600-foot runway, that's not a problem. But try this at an 1,800-foot runway, and you very well may have it. Now, in addition to the absolute weight of the aircraft, we also experience G loads from two sources, one of which is maneuvering. So if we engage in a coordinated turn, we experience G loads that are greater than 1. And what that means is that as we increase our bank angle, the G loads we experience also increases. Forget the equations. Basically, the lift from the wing is normal to the wing, perpendicular. And in order for the vertical component, which is the blue arrow, of the lift, in order to equal the weight, if those two are equal, then we will not be experiencing a vertical force in either direction. We'll maintain a steady 0-degree rate of climb. But the more we bank, the greater our bank angle, the greater the g-force that we will experience. So, for example, if we're engaged in a 45-degree bank, we will be pulling 1.41 g's. Now, what is the significance of that? Well, the wing doesn't know whether the lift it has to produce comes from the absolute weight of the aircraft or the g loads, but if we're flying 1.4 g's, the wing has to generate that much more lift. And so if we're flying at 0 bank angle, or 1g, our flap stall speed is 61 miles an hour. If, on the other hand, we're pulling 1.4 g's in a 45-degree bank angle, our stall speed increases to 72 miles an hour. Now, let's say we're flying straight and level, and we're flying, let's say, at 68 miles an hour, so it's not much of a margin over stall, but at least we're overstalled, we're not stalled. If we suddenly go into a 45-degree bank and pull 1.4 g's, we will stall. And in a few minutes, I'll show you a video clip of exactly that scenario. And in that case, the pilot did an accelerated stall at only 1.2 g's, so it's pretty dramatic. And where that often happens is in that base to final turn. This is a well-known area where accidents occur, loss of control accidents, somewhat like we saw in the initial video. If we're flying a left-hand pattern and we're doing a standard base to final turn, the shaded area represents the extended runway centerline. And if we have a direct headwind, that's pretty easy to handle. If we're flying a left-hand pattern and we have a crosswind from the left, as you see here, it's quite easy to misjudge that turn. And if we get blown past the runway centerline, we have no choice really but to increase our bank angle in order to turn back and get on centerline. When we increase the bank, we increase our G loads. And if we're close to stall speed, if we're not careful, we can stall. And unfortunately, that's a pretty common accident scenario. The other place we see G's is from turbulence. So there are gusts, both horizontal and vertical, and they affect G loads as well. If we're flying in calm conditions and we're flying along at a certain speed, the relative wind is shown by this green arrow, and we're flying at a certain angle of attack. However, if there are vertical gusts, in this case I've shown an up gust, the relative wind is now a combination of the vertical gust velocity and the relative wind. So the actual relative wind at this instant is what's shown with the blue arrow. And as you can see, that basically instantaneously changes our angle of attack. When we increase the angle of attack, we increase the lift that's generated by the wing. And as long as we're below stall, we will essentially feel an additional G-force. Those are basically the G's we feel during turbulence. We feel these vertical G's, and that's what's happening here. And in fact, even in what's defined as light turbulence, the variable vertical component of G that we can see is up to half a G. So our normal condition is 1 G. If you superimpose plus or minus half a G, we can be pulling 1.5 G's just due to turbulence. And obviously, turbulence is not predictable. And of course, the more significant turbulence, we can actually pull up to 2 G's. So we get G's both from the maneuvering and from turbulence. Now, recently, Laura and I were flying. I was taking some dual from Laura. And these are the conditions that we were flying. Our max gross weight, or pilot operating handbook, says at 2,450 pounds, our stall speed in the clean configuration is 68 miles an hour, true, at 1 G. We were not at max gross weight. We only had 2 people. We did have full fuel, a few bags. So we were below gross weight. And if you do the calculations, that says that our 1 G stall speed with the flaps up is 64 miles an hour. These are the actual G's that I recorded on my cell phone during about 5 minutes of flight. And you can see that it bounces around quite a bit. And this was not a turbulent day at all. It was pretty calm. But during those 5 minutes, and I was doing some maneuvers, including some steep turns, and during this particular 5-minute segment of flight, we experienced a maximum of 1.53 Gs and a minimum of 0.6 Gs. So this is kind of normal in flying. Our average, as you might expect, was just about 1 G. But since we know the Gs, we can convert that into the equivalent stall speed at that instant in time, which is what I've done here. And this is what the stall speed looks like during that 5-minute segment of flight. And so even though our mean airspeed at 1 G is 64 miles an hour, during this period of flying, we actually had a stall speed as low as 50 miles an hour or as high as 79 miles an hour. So the G loads and the aircraft weight have a big influence on our stalling behavior. So let's review what we've talked about so far. First of all, the airspeed indicator already compensates for density altitude. That's a good thing. But what it does not account for is the actual weight of the aircraft, the G's from maneuvering. We can calculate those and use rules of thumb, although many people don't. But also the G's from turbulence, and there's no way you know what the turbulence is going to be. You know if it's light or whatever, but you don't know what gust will hit you and when. So what we really want is a single instrument that tells us where we are with respect to the ability of the wing to generate lift. And in fact, that is exactly what an angle of attack indicator does. So, again, last time I'll show you this curve. What we're plotting here, power required, is the horsepower as a function of the true airspeed. And we're doing this at maximum gross weight. Every one of these speeds corresponds to a very specific angle of attack that the wing is flying. And so if we plot the horsepower versus angle of attack instead of versus speed, this is what the curve looks like. By the way, this curve, as we've said, will change as the airplane weight changes and the G loads change. But if we look at those angles of attack and plot those, this is what the power required curve looks like as a function of the angle of attack. So a couple of things worth noting. First of all, the wing is operating, in this case, over about an 18-degree operating range of angle of attack. But if you look at these key performance points that we're interested in, they occupy about 75% of the range, and they are much better separated in the angle of attack regime than they are in the airspeed regime. So if we have an accurate angle of attack indicator, it's easier to hold these specific flight conditions using angle of attack than it is using airspeed. But that's one thing, it's easier to hold. But the more important thing is that this curve, unlike the airspeed curve, this curve never changes. Doesn't matter what the airplane weighs, doesn't matter how many G's you're pulling. The airplane with flaps will always stall at 17 degrees angle of attack, regardless of what the weight is, regardless of what the G forces are. If we want to fly max L over D, that occurs at 3.5 degrees angle of attack, regardless of these other conditions. And that's the true beauty of the angle of attack indicator. So the angle of attack for these conditions is the same for all conditions. And as we've said, those conditions change continuously. So it makes it much simpler for us to operate where we want to operate by looking at one instrument that is not affected by those factors. And as I mentioned, we can hold those conditions better with angle of attack than we can with airspeed. Now, the FAA recognizes the value of angle of attack. A little over a year ago, they came out with what they call an SAIB, a Special Airworthiness Information Bulletin, that addresses angle of attack indicators. And I'll let you read what they had to recommend. So what the FAA is saying, or recommending, is that all operators of aircraft install and train and use an angle of attack system. Now, this is a recommendation only. It's not a requirement. But the fact that they put this in writing and define it as their official policy is done for a reason. They're trying to enhance aviation safety because they believe that angle of attack is a better way to control the airplane in certain scenarios. Now, at this point, you may be saying to yourself, Dave, you've made the case that angle of attack could be helpful in our flying, but what are we supposed to do? We don't have an angle of attack indicator in our aircraft, and of course that's true. However, today there are 6 or 7 companies that offer affordable, accurate angle of attack systems that can be put into the airplane. The way the FAA wants to see these things is used as supplemental sensors only. And what that means is they can't tie into anything on the airplane that was part of the aircraft certification. So, for example, you can't take a tap off the pitot tube in order to feed your AOA system. It has to be independent. And once you decide you want to put one of these in your airplane, the FAA considers it a minor alteration, which means that you only need to create a logbook entry to document that the aircraft has changed. If it were a major alteration, you'd have to fill out a 337. So that is not required in order to retrofit an AOA system into your aircraft. The FAA defined two memos that define what they believe a good AOA system has to comply with. The first one is specific to angle of attack. That memo has later been broadened, and the earlier memo was superseded. And the current memo that defines this is something that's referred to as NORSI, which is non-required safety enhancing equipment. So this memo is the FAA statement that says if you want to install something that enhances safety, here's what we think you need to do in order for us to bless it. So an AOA system manufacturer, like one of these companies, submits a documentation package to the Chicago certification authorities. They have responsibility for NORSI equipment. And the FAA, if they believe that the equipment complies with what they think it needs to comply with, will issue them a letter saying, we believe your system meets the requirements of the NORSI memo. So any one of these companies will publish those letters on their website. It's somewhat similar to an STC, but it's not an STC. We can go into that later if anybody is interested. An AOA system has two components. It's got the sensor, where the raw data that's used to calculate angle of attack is acquired, and then it's got a way of presenting what the AOA is to the pilot, and there's several ways to do that. If we start by looking purely at the sensor, most of them use a device that looks like a regular pitot tube, and it has a dynamic pressure port in the front of the pitot tube, but it also has a second pressure port, and that's typically on an angled surface. Often the angle is at 45 degrees. And it turns out that if you take the dynamic pressure, the pressure from the angled surface, and the static pressure, which can be derived from either a port on the probe or elsewhere, the ratio of those three sensors can be used to very accurately determine what the angle of attack is. There are other systems out there. A company called SafeFlight, which has been around for a long time, has a sensor that looks very similar to what we're already familiar with, which is a stall warning switch that's on the leading edge of the aircraft, and it has a tab like our switch, and that tab moves with the stagnation point of the airflow of the wing, and that stagnation point will move with different angles of attack. The switch that we have is a binary device. It's either on or off. It's obviously set to go off 5 knots above the stall speed. But the difference is that this is not a binary switch. This is an analog switch, or an analog device. And so whatever position this vane has determines exactly what the angle of attack is, and that information is fed back to the indicator. If you look at the displays or the indicators, how does the pilot know what the angle of attack is? That varies as well. There are two groups of sensor displays. There are visual displays. Here you see sort of a standalone display. This particular one happens to come from Garmin. Or that information can be displayed on an EFA screen, as you see here, where the yellow arrow is pointing. This particular EFA screen is from Dynon. Garmin has a G3X EFA screen, and the AOA system from Garmin will integrate with the G3X. So that's one way that AOA can be displayed to the pilot. But the other way is that you can get audio feedback. And there's certain benefits from doing that. First of all, it turns out that your brain takes much longer to process visual information and sort of understand what that information means than it does to process audio information. It takes about 3 times as long. So that's one benefit of audio feedback. But the more important benefit is that if you're relying on audio feedback, that means you don't have to increase your instrument scan to include another thing to look at. And since most of the loss of control situations occur at low speed in the approach and landing, you want your eyes outside the cockpit, and relying on the audio for angle of attack is a nice way to do it. So in the rest of the presentation, I'm going to focus on the audio, although you will also see some of the visual indicators in some of the video clips that I'm going to show you. So let's start by simply hearing what the audio indication looks like. And in this particular video, there'll be some text that appears on the screen as the audio signals change, indicating what's going on. So that was what it sounds like. In this video, you're going to hear the narration of the pilot. The pilot is Mike Piccaro. Mike is the president of Fly On Speed, which is a volunteer nonprofit organization that I'll talk more about at the very end. And so he's going to narrate what the tones are, what they mean. But in addition to that, you're also seeing on the lower right-hand side an inset of what this visual indicator is showing. And I want you to pay attention to the symbology in the center of that display. There's a lot of information being presented here, but the symbology is what tells you what the angle of attack is. And in order to describe that, let me show you this curve. And what we're doing here is showing you what happens as you start at some sort of a cruise speed, for example, above the maximum L over D. And as you progressively slow down, this is what the symbology does. So, for example, you're above the max L over D speed, let's say you're at cruise, the entire display symbology is not lit up. You'll notice there is a white bar here, and there are two dots. When you slow up enough to where you hit the maximum L over D angle of attack, that bar lines up with these two dots, but at the same time, the lower two portions of the chevron light up in blue. So that means you're at this particular indication, you're at maximum L over D. That's where it goes off. As you continue to slow up, the bar continues to go up, and in fact, as you get close to on speed, the lower half of the green circle will light up. That means you're still above on speed, but you're getting close. When you actually are on the on-speed angle of attack, the bar is straight across the green circle. The green circle is fully lit, and that's how you know that you're on speed. And the corresponding audio signal, and you'll see this in the videos, is a steady tone. As you continue to slow up below on speed, the upper chevron lights up in yellow, and that bar, which represents the angle of attack, continues to go up. And as you continue to slow up, that bar goes up, and the chevron turns from yellow to red. And finally, when that bar hits the top, is when you stall. So that sequence is shown here.
All right, let's take a quick look at how the tone works. We'll just pull our power back, decelerate, increase our angle of attack. Tone's going to start at an elevating max condition, which is a peak performance parameter. 400 hertz tone. It's going to have a variable pulse rate. So as I decelerate, the pulse rate's going to increase, which tells me I'm increasing my angle of attack. Once I get to an on-speed condition, the tone's going to go steady. Now, on-speed in this airplane is a plus or minus 1 degree AOA band. That works out to an airspeed band of about plus or minus 2 knots of an actual on-speed condition at 1G. Now, if we continue to increase angle of attack and continue to slow down, we get a distinct frequency change in the tone. And notice that the pulses start again giving me trend information as we decelerate into the stall. Once we get to a stall warning, we get a very distinct 20 pulse per second tone that's designed to mimic the sound of a stick shaker or a pedal shaker and provides our normal FAR 23 stall warning criteria.
Now, this sequence is not flown by Mike. It's a different pilot that has an AOA system. It's got the same visual indicator up here. This one doesn't have the inset in the video. But what this is showing is how the audio indication of the AOA system sounds during a well-executed normal approach. During the approach, you should fly it at VREF or on speed. That means the tone that you'll hear is steady throughout the approach. And then as the pilot starts to flare, you'll hear the indications that he's approaching stall. I apologize in advance in the sense that this is a pretty boring video because all you're hearing is a steady tone. He starts this sequence just before he's turning his downwind to base leg, and it ends with him with touchdown. So let's hear what that looks like, or sounds like.
Base traffic, 8 Tango Lima is turning base, full stop runway 10. Base traffic, spin on 8 Tango Lima is turning final, full stop runway 10.
Now, mentioned earlier that angle of attack has nothing to do with the particular attitude that you're at or the airspeed that you're at. And in order to demonstrate this, what Mike is showing you in this little video clip is he's actually performing a split S maneuver where both the airspeed and the attitude of the airplane are changing radically. But he's intentionally flying this at a constant angle of attack. He happened to have chosen to fly it at on speed. There's nothing special about flying it at a split S at on speed. He's just showing you that you can maintain a given angle of attack regardless of what the airspeed and the attitude of the aircraft are. So let's take a look at that in this video clip.
But before we do that, I want to talk just a little bit about what an on-speed condition is. Now, remember, on-speed is an angle of attack. It's not an airspeed. Okay? And we can be on speed at any airspeed and any attitude. Now, right now, I'm just at straight and level flight, and I'm at a VREF condition, and that, in fact, is on speed. But I can also maneuver on speed. I can split S on speed. So obviously my airspeed is changing dramatically, but I'm flying the same angle of attack throughout the maneuver.
What Mike is doing in this next video clip is he's simulating a base to final turn. And even though the G's that he's experiencing during this turn are pretty small, you will see that he actually stalls the aircraft with a very small increase in G load. In fact, first of all, you can see the airspeed indicator here. You've probably noticed that before. One of the things that you may have seen is that the visual indicator also includes a G level recording or output. And you'll notice that when he stalls, he's only at 1.2 Gs. So let's take a look at that video clip.
So, and let's just set up for a common traffic pattern. So let's just slow the airplane down. We'll deploy flaps 40 because that's the way we land this airplane. We'll go to an on-speed condition because that's the way that we land the airplane, okay? And then we'll just roll into a base turn and we'll depart the airplane.
So as you can see, there's very little buffeting or attitude variation or airspeed variation that would let you know that you're about to enter a stall. However, in the audio tone, you can hear that angle of attack tone telling you, hey, you're getting close to stall. So that audio information should enable you to recognize that you're getting close to stall and to act accordingly. This is the last video clip, and this is a maneuver that I would certainly not recommend people try to simulate. Obviously, Mike is a good pilot. He is an airline pilot. He was a Navy fighter instructor pilot. So part of the reason he's able to pull off this maneuver is because of his piloting skill. However, the other part of it is that he's using the angle of attack meter to do the impossible turn as efficiently as possible. It turns out that you can get the best turning performance, no matter what your power level is, by flying at the on-speed condition. In fact, fighter pilots use it because it allows them to optimize their turning performance when they need it, such as in a dogfight. Dogfights don't happen really that much these days. But the point is that if you fly your turns at on-speed condition, you get the most efficient use of the energy that you have. What I'm also showing you here is the altimeter of this airplane. The reason I'm showing it to you is that during the flight, the instrument panel is sort of in shadow, and so it's difficult to see. The field elevation where Mike is operating here is about 250 feet. You'll barely see, the altimeter shows that he cuts the power actually at 500 feet MSL, but then he counts to 3, and the reason he does that is to simulate what's called the startle factor. It typically takes a pilot about 3 seconds when some anomalous behavior occurs for them to recognize and start to react to that. So at 500 feet MSL, he'll start to count out 1 Mississippi, 2 Mississippi, 3 Mississippi, and by the time he finishes that count, he's actually right here at 550 feet. So he's doing the impossible turn from a start that's 300 feet over the ground, and let's see what that looks like.
Skypark traffic, RP7 Bravo, departing runway 9er, simulated engine failure on takeoff, immediate return 27, Skypark. 1001, 1002, 1003. Lift flaps. On speed.
So he's initiated a right turn, and he has a heading change of 215 degrees to make, but he's doing it on speed.
.45-degree angle for the reposition.
And now he's performing a 45-degree entry back to the runway. So again, not a maneuver I would recommend, but what I'm hoping to illustrate with this clip is the fact that you can perform, you can have the aircraft perform at its optimum performance level by relying upon the information that an angle of attack indicator gives you. So let's summarize. First of all, loss of control is a significant contributor to general aviation accidents. AOA information can help you avoid getting into a loss of control scenario. And AOA is also very helpful for other flight conditions that occasionally we want to operate at. The FAA understands this. It's their official policy for about a year now to encourage pilots and aircraft owners to install and use AOA systems. And there are a lot of companies out there that sell good AOA systems that are affordable and accurate. So my main goal in presenting this is to plant a thought in your mind that says, hey, is it worthwhile for us to think about putting an AOA indicator in our aircraft? I do want to acknowledge the contributions from an organization called Fly On Speed that Mike Vaccaro heads. It's a nonprofit, all-volunteer group. All of their work is open source, and so what they're trying to do is enable the experimental aircraft community to build their own AOA system. Initially it was focused towards RV builders, but it's broader than that. And because these are supplemental systems, they don't need to be qualified by the FAA, and it's certainly something that can be considered for certified aircraft. Although there are many commercial FAA, I'll use the word certified in quotes, systems available. So Mike is the sort of prophet of AOA, and I'm simply helping him to expand his reach in terms of the importance of AOA to the general aviation community. And so with that, I am happy to answer any questions you guys might have.